my name is Dana Golden. Today we're going to talk about algorithms and computational complexity for the data science and machine learning course. So what are algorithms? Algorithms are a finite set of well-defined instructions to solve a problem or perform a task. Basically, you give a set of instructions. Think of it like if you give it to a toddler. You say, do this, then do this, then do this, and the task will be complete. So the foundation of data science, they help us clean, build models, and make decisions. So you can sort a list, you can predict housing prices, and you can group similar items. So just some things you can do. So some types of algorithms, brute force algorithms, you try all possible solutions. This is usually pretty inefficient, but there are some places where brute force works really well. You have greedy algorithms, where you try to make locally optimal choices at each step. Gradient descent is an example of a greedy algorithm. This is often fast, but may not yield the global optimum. You have divide and conquer algorithms. This is like recursion, where you break problems into subproblems and you solve recursively. So you make it a little bit smaller, and then you solve the small problem, and then you use a bunch of those small problems solve the big problem. Dynamic programming is you solve overlapping subproblems and you store the solutions. This is usually in coding interviews, this is what you get asked about because it's a very fast, much more efficient way to solve problems. And then backtracking, systemically search for solutions and undo steps as needed using puzzles and constraint satisfaction. So the problem is sorting. Rearrange a sequence of items so they appear in a specific order, usually ascending or decreasing. So you start with a list of array elements, and then you output a new list where the elements are sorted. So it enables faster searching, helps organize data, and often is a pre-processing step in data science and machine learning. So here is bubble sort. Bubble sort is an algorithm where you repeatedly step through a list, compare adjacent elements, and swap them if they're in the wrong order. So this takes complexity and squared. It's easy to understand, but inefficient for large data sets. Merge sort uses the divide and conquer strategy and recursively splits the list, sorts the sublist, and merges them. It's much more efficient, and it's often used in real-world applications. Neither of these are the most efficient for all problems, but merge sort is very efficient for most problems compared to bubble sort. So step by step, you start at the beginning of the list. You compare each pair of adjacent elements. If the elements are in the wrong order, you swap them. You move one right before the other. Repeat the process for the entire list. And after each pass, the largest unsorted element bubbles up to its correct position. You continue until no swaps are needed. So you have pass 1, and so you start with this 2, you switch it with this 4. Then you have this sorted list, and so you don't need to do anything else, so you have a sorted list. So each pass moves the next largest number to the right place and gets sorted after one iteration. Merge sort, if the list has 0 or 1 elements, it's already sorted. Otherwise, divide the list in 2 halves, split it up, recursively apply merge sort to both halves, merge the 2 sorted halves into a single sorted list, and continue until the full list is merged and sorted. So you split up into 2 halves, 2 slightly smaller halves. You split again, and then now you have 1 and 4, 2 and 8, and then you merge 1 and 4, and then you merge 1, 4, and 5, and then 2 and 8, you merge to 2 and 8, and then now you have 1, 4, 5, and 2 and 8. So now it becomes 1, 2, 4, 5, 8. Here you're doing divide and conquer. So you're splitting it up repeatedly. Dynamic programming is another example of an important algorithmic process. It's a method for solving complex problems by breaking them down into simple or overlapping subproblems and storing their solutions. So the idea of optimal programming includes an optimal substructure. An optimal solution can be composed from optimal solutions or subproblems, and an overlapping subproblems recur and can be cached or memoized. So you characterize a subproblem, you recursively define the value of the optimal solution, you compute the subproblem solutions bottom up or top down, you can construct the overall solution. So value iteration macroeconomics. Macroeconomics is famous for using value iteration using the Bellman equation. So V of S equals max of the utility function plus beta times the expected value of the value function tomorrow. So you start with an initial guess, you iterate on the initial guess and continue until the difference between the value functions is below tolerance. You can use this in Arigari models, Ramsey growth models. So value iteration algorithm, top-down plus minimization. You initialize an empty cache for V of S. You compute value of S. If S is in cache, return cached V of S. For each feasible solution A, you do Q of SA equals U plus beta compute value of S prime, and then you get the value function is equal to max of Q of SA, and then after convergence for each node, choose argmax of S. This is an example of memoization because you're storing the value function, you're updating it as a table. So value iteration is dynamic programming. You have an optimal substructure, which is the decision in state S, which uses the optimal continuation value V of S prime. Overlapping subproblems, many calls to E of V S prime across states, and you have states, actions, and transition. Value function update is a dynamic programming recursion. So as a visual, you have this table, and you're just updating through iterations. So types of algorithms in data science, you have supervised learning, unsupervised learning, reinforcement learning, optimization algorithms. Supervised learning, you have an input and output that are known. Unsupervised learning, you only know the input data and you find patterns. Reinforcement learning, you learn by interacting with the environment. And optimization algorithms, you improve a function or performance manager like gradient descent or genetic algorithms. And that's our introduction to algorithms. Thank you.